Hello my friends and welcome to my channel. Walter here, and today I'll be taking you through the Further Pure Maths 1 paper, that's paper 13 of the May-June 2023 sitting. For more learning resources, you can visit my website waltermaths.com. Here you'll find links to my courses, live classes and much more. And just for watching this video, I have a special gift for you, which is this revision ebook, which you can download from the link which is in the description. So I hope you're gonna learn a lot from this video, and let's get started. So let's start with question number 1. It says, prove by mathematical induction that for all positive integers n, 5 to the 3n plus 32 to the n minus 33 is divisible by 31. Alright, so to answer this question here, we are going to start by saying, let Pn be the proposition that 5 to the 3n plus 32 to the n minus 33 is divisible by 31. So first of all, we are going to start by proving for n is equal to 1. So the statement P1 is when n is equal to 1. And when n is equal to 1, we will be having 5 to the 3 of 1 plus 32 to the 1 minus 33. And this gives us 5 to the 3, that's 125. And that's plus 32. And that's minus 33. And here we get 124, so 124 here. Now 124 is divisible by 31, and therefore P sub 1 is true. Let's go on to P sub k. Here we are assuming that the statement is true when n is equal to k. So we assume that 5 to the 3k plus 32 to the k minus 33 is divisible by 31. Now, if this is divisible by 31, this has to be equal to 31 of a constant, so 31m. Next up, we are now proving for n is equal to k plus 1. So the statement P sub k plus 1 will be 5 to the 3 of k plus 1. And that's plus 32 to the k plus 1 minus 33. So we want to see if this statement will be true again. All right. So we can simplify this to, this will be 5 to the 3k plus 3. And that's plus 32 to the k plus 1 minus 33. All right. Now this is as good as 5 to the 3k of 5 to the 3 plus 32 to the k of 32 to the 1, and that's minus 33. This is equal to 125, because 5 cubed is 125, of 5 to the 3k, and that's plus 32 of 32 to the k, and that's minus 33. All right. Now we're going to split 125 into 124 plus 1. So that's multiplying 5 to the 3k. And we're also going to split 32 into 31 plus 1, and that's of 32 to the k, and that's minus 33. So we can now simplify this, and we will now have here 124 of 5 to the 3k, and it's plus 5 to the 3k, and that's plus 31 of 32 to the k, and that's plus 32 to the k, and minus 33. All right. Now we are going to rearrange. So we'll be having 124 of 5 to the 3k, and I'll take the 31 of 32 to the k, and I'll have remaining the 5 to the 3k plus 32 to the k minus 33. All right. Now, I think you can see here that this part is what we got on our assumption step, where we say that 5 to the 3k plus 32 to the k minus 33 is equal to 31m. In other words, we say that it is divisible by 31. And I'm also saying here that this part, again, is divisible by 31. So we can say here 31 factored out for these two terms will be 4 of 5 to the 3k, and it's plus 31, and it's plus this one here, we got it to be 31m. And here I'll say let L be equal to the 4 times 5 to the 3k plus 31, such that we will now be having 31L plus 31M, which is a thing that is divisible by 31. So we get 31 of L plus M. So this thing is divisible by 31. And so, since we've proved that P sub k plus 1 is true, we can say that by the principle of mathematical induction, it is going to be true for all positive integers n. And that's how we prove this by mathematical induction. All right, let's go on to the next question. On question 2, it says, use standard results from the list of formulae MF19 to show that the sum from r is equal to 1 up to n of 6r squared plus 6r minus 5 is equal to an cubed plus bn squared plus cn, where a, b, and c are integers to be determined. All right, so here we have the sum from r is equal to 1 up to n, and that's of 6r squared plus 6r minus 5. And this is equal to 6 of the sum from r is equal to 1 up to n of terms of the form r squared plus 6 of the sum from r is equal to 1 up to n of terms of the form r, and that's minus the sum from r is equal to 1 up to n of 5. All right. Now, if you use your standard results from the list of formulae, you will get that the sum of terms of the form r squared comes out as a sixth of n plus 1 of 2n plus 1. And that's plus, for the sum of terms of the form r from r is equal to 1 up to n, here we'll get 6 of half n of n plus 1. And that's minus 5n. All right, so we can divide 6 into 6 and we get 1. So here we'll be having n of, expanding the brackets here, that's 2n squared plus 3n plus 1, and it's plus. Here we can divide 2 into 6 and we get 3. So we'll be having 3n of n plus 1, and it's minus 5n. All right, so simplifying this a little bit more, we'll be having here 2n cubed plus 3n squared plus n, and this plus 3n squared plus 3n minus 5n, and we will get 2n cubed, then 3n squared plus 3n squared is 6n squared, then n plus 3n is 4n, and minus 5n, that will be minus n. So what we have here is the answer to part A. Let's move on to part B. It says, use the method of differences to find the sum from r is equal to 1 up to n of terms of the form 6r squared plus 6r minus 5 over r squared plus r in terms of n. Alright. Now, looking at what we have here, we can express this as the sum from r is equal to 1 up to n of 6r squared plus 6r over r squared plus r, and that's minus 5 over r squared plus r. Okay, so we can express it this way so that we can actually simplify it, and here we'll be having for 6r squared plus 6r, we can actually factor out 6 so that we have r squared plus r, and that's over here at the bottom, that's r squared plus r, and that's minus 5 over, and this is r squared plus r. Alright, so we have this thing here, and we can actually cancel out this so that we will be having the sum from r is equal to 1 up to n of 6 minus 5 over r squared plus r, which is as good as r of r plus 1. So here we're going to say this is equal to the sum from r is equal to 1 up to n of terms of the form 6, and it's minus, and here I factor out the 5, and it will be the sum from r is equal to 1 up to n of 1 over r of r plus 1. So we want to express this in partial fractions. Alright, so I'm going to say here, consider 1 over r of r plus 1, and we know that it will be equal to, in partial fractions, a over r plus b over r plus 1. Alright, and as an identity, we'll be having 1 being equal to a times r plus 1, so it's a of r plus 1 plus br. So if r is equal to 0, we'll be having 1 being equal to, here it will be 0 plus 1, which is 1 times a, it's a, and b times 0 here will be 0. So we're getting that a is 1. And when r is equal to minus 1, here we'll be having 1 being equal to minus 1 plus 1, that will be 0. So this whole thing becomes 0. And here it will be b times minus 1, which is minus b. So we're getting that b is equal to minus 1. So we can therefore say 1 over r of r plus 1 is the same as a, which is 1 over r, plus b, which is minus 1 over r plus 1. Alright, so if we are then going to say the sum from r is equal to 1 up to n of 1 over r of r plus 1, it will be equal to the sum from r is equal to 1 up to n of terms of the form 1 over r minus 1 over r plus 1. Alright, this whole thing here. And we can now apply the method of differences, where we're going to say here, when r is 1, we'll be having 1 over 1, which is 1, and it's minus 1 over 1 plus 1, which is 1 over 2, right? And it's plus, when r is 2, that will be 1 over 2 minus 1 over 2 plus 1, which is 1 over 3. When r is equal to 3, it will be 1 over 3 minus 1 over 4, and so on. For now, when r is n minus 1, that's the second from last term, it will be 1 over n minus 1, and here it will be minus 1 over n minus 1 plus 1, which will be 1 over n. Lastly, for the very last term, where r is n, it will be 1 over n minus 1 over n plus 1. Alright, now I think you can see here that the terms on the inside add up to give us 0, like this too. So these add up to give us 0, minus a quarter will add up with a quarter to give us 0, and this will have another term to add to it, and so give us 0. These two again add up to give us 0. So we are basically left with 1 minus 1 over n plus 1. All right, so this is what we'll be having here for the sum of 1 over r of r plus 1, which is this part. So if we bring this back, all right, if we bring this back, because this is what we were evaluating, and we place it down here, I'll say therefore this is equal to, we know that the sum of 6 from r is equal to 1 to n will be 6n, and that's minus 5 of, here we've gotten it to be 1 minus 1 over n plus 1, so it's 1 minus 1 over n plus 1, like this. So we have 6n minus 5 plus 5 over n plus 1. So this is what we get right here. That's the answer to part B. So let's move on to part C. It says, find also the sum from r is equal to n plus 1 up to 2n of terms of the form this in terms of n. All right. Now, what you need to understand here is when we are looking for the sum from n plus 1 to 2n, it is as good as, here let's say we have the first term, that's term number 1, term number 2, term number 3, and so on, up to term number n. After term n comes term n plus 1, and we continue to go, and along the way we'll reach to term 2n. So when asked to find the sum from n plus 1 up to n, like they have asked us, we can say it's as good as from 1 up to 2n minus from 1 up to n. Okay, so it's the same thing. So basically what I'm saying here is the sum from r is equal to n plus 1 up to 2n of terms of this form is equal to the sum from r is equal to 1 up to 2n, all right, of terms of the same form, and that's minus the sum from r is equal to 1 up to n of terms of the same form. Okay, so this is what we're going to be using. All right, now we had obtained the sum to n, okay, of terms of the same form. Okay, that's what we're being asked for on part B, and we got that to be 6n minus 5 of 5 over n plus 1. So here I'll say, since we had gotten the sum to n to be 6n minus 5 plus 5 over n plus 1, we can therefore say the sum to 2n will be 6 of 2n minus 5 plus 5 over 2n plus 1, and it's minus the sum to n. This is just the sum to n, the one we have already, which is 6n minus 5 plus 5 over n plus 1. All right, so this is what we have. So we need to simplify this. So we have here 12n minus 5 plus 5 over 2n plus 1, and it's minus 6n plus 5 minus 5 over n plus 1. All right, and this will be 12n minus 6n is 6n. Then we have the minus 5 plus 5, that's 0. Then it's going to be plus this, which is 5 over 2n plus 1, and it's minus this 5 over n plus 1. So what we have right here is the final answer. Let's move on to the next question. It says the equation x to the 4 minus x squared plus 2x plus 5 equal to 0 has roots alpha, beta, gamma, delta. So on A, find a quadratic equation whose roots are alpha squared, beta squared, gamma squared, delta squared, and state the value of alpha squared plus beta squared plus gamma squared plus delta squared. Alright, so here I'll say let y be equal to x squared, such that x will be equal to y to the power of a half. Alright, so therefore the equation we have, substituting y to the half for x, it'll be y to the half to the power of 4 minus y to the half squared plus 2y to the half plus 5 equal to 0. This gives us y squared minus y plus 2y to the half plus 5 equal to 0. Okay, now I'm going to make the 2y to the power of a half subject, and that will be equal to, taking everything to the other side, minus y squared plus y minus 5, like this. Now we want to get rid of the power half, so I'm going to square both sides from here. So square both sides here and square both sides here. If we do that, we'll be having on the left side 4y, and here I'll treat this 2 as 2 elements. So basically expanding them, we'll be having minus y squared, which is y to the 4, and that's going to be plus 2 times minus y squared of y minus 5, and that's going to be plus the last term squared, which is y minus 5 squared, right? So that's 4y is equal to y to the 4, and here that'll be minus 2y squared of y minus 5, and that's plus y minus 5 squared. So let's now expand the brackets. So we have 4y here being equal to y to the 4, and here we'll be having minus 2y cubed, and it's plus 10y squared, and expanding this bracket we get y squared minus 10y plus 25, right? So that is, if we take everything to one side, we are left with 0 on the left, and we have y to the 4 times in y cubed, that's minus 2y cubed, times in y squared, that's 10y squared, plus y squared, which is 11y squared, and here we have minus 10y minus 4y, which is minus 14y, and is plus 25. So this is what we'll be having. So we can write this as y to the 4 minus 2y cubed plus 11y squared minus 14y plus 25 equal to 0. So that's the answer to part A. Let's go on to part B. On B, they say, find the value of 1 over alpha squared plus 1 over beta squared plus 1 over gamma squared plus 1 over delta squared. All right. Now, for what we have here, we can say it's equal to, and here we have a common denominator, which is alpha squared, beta squared, gamma squared, delta squared. And with this common denominator, on the numerator we'll now be having beta squared, gamma squared, delta squared, and it's plus alpha squared, gamma squared, delta squared, and it's plus alpha squared, beta squared, and delta squared, and it's plus alpha squared, beta squared, gamma squared. So we actually have the sum of product of triples over the sum of roots, and that is of this particular polynomial that we got. Okay, remember the roots of this polynomial are alpha squared, beta squared, gamma squared, and delta squared. So I'm going to take this and I'll paste it here, okay, where we can see it. So for this, we can say that the sum of roots, I can write them as sum of roots. So since the roots are squares, we can say that the sum of roots is minus b over a, which is 2, the sum of pairs, product of pairs, okay, which I can write this way, is actually b over a, which is 11. Then the sum of product of triples, which I can write this way, is minus c over a, which will be 14. And lastly, the product of roots will be d over a, which is 25. All right, so here we have the sum of product of triples, which is 14, and that's divided by the product of roots, which is 25. So this here is the answer to part B. Let's go on to C. They say find the value of alpha to the 4 plus beta to the 4 plus gamma to the 4 plus delta to the 4. Right, so this is more like the squares of the roots that we had. It's as good as alpha squared plus beta squared plus gamma squared plus delta squared. So for this, we know that this gives us the sum of the roots squared minus 2 times the sum of the product of pairs of the roots. All right, so in our case, the sum of the roots is 2, so it's 2 squared, and it's minus 2 of the sum of product of pairs. We have that to be 11, so 11 here, so it's like 4 minus 22, okay, which is minus 18. So that's the answer to part C here. So that's how we do it for this question. Let's move on to the next one. Now we're looking at question number 4. It says the matrix M is given by M is equal to cos 2 theta minus sin 2 theta, sin 2 theta, cos 2 theta of 1, k, 0, 1, where theta ranges between 0 and pi, and k is a non-zero constant. The matrix M represents a sequence of 2 geometrical transformations, one of which is a shear. So on part A, describe fully the other transformation and state the order in which the transformations are applied. All right. Okay, so here we have 2 transformations represented by the matrices. And to write down the order in which the transformations will be applied, we start with the second matrix, which represents the first transformation. So this matrix here represents a shear where the x-axis is invariant and the shear factor is k. The second transformation is represented by the first matrix, and this is a rotation by an angle 2 theta and about the origin, and this is actually an anti-clockwise rotation. So that's how we describe these 2 transformations. All right, let's go on to part B. It says write M inverse as the product of 2 matrices, neither of which is I. All right, so in this particular case, we're going to use the fact that if you have the product of 2 matrices, say AB, the inverse of AB is equal to B inverse multiplying A inverse. Okay, so this is an important rule. So we can take what we have here, the matrix M, to be 2 matrices A and B. So basically we are saying AB inverse is equal to B inverse pre-multiplying A inverse. All right, so let's make use now of the matrices we have. When we say AB inverse, that's like M inverse, and that's equal to B inverse, which means B inverse would be the inverse of the second matrix. So for the inverse of this matrix, we have to find the determinant, which will be 1 times 1 minus k times 0. So it's just 1. Then we will switch the positions where it's 1, so it doesn't matter. And for these ones, we multiply by minus 1. So we'll be having minus k there. So the inverse of matrix B comes out as 1 minus k 0, 1. All right. Next up, we have the matrix A. And for its determinant, we're going to say 1 over the determinant of A. Okay. And we multiply that by a matrix where we switch positions for this diagonal, where since they're just cos 2 theta, they will remain cos 2 theta. And we multiply by minus 1 these elements. So we'll be having here sine 2 theta and minus sine 2 theta here. All right. Now, the determinant of A is cos 2 theta times cos 2 theta, which is cos squared 2 theta, and it's minus sine squared 2 theta. So it's as good as we have cos squared 2 theta plus sine squared 2 theta, which is 1. So eventually here we will have 1 minus k 0, 1 multiplying cos 2 theta sine 2 theta minus sine 2 theta and cos 2 theta. All right, so this is what we have here. That's M inverse as the product of two matrices. All right, let's go on to part C. They say, find in terms of K the value of tan theta for which M minus I is singular. All right, so here we're talking about M minus I. All right, the matrix M is the product of these two. So let me write it down. That's cos 2 theta minus sine 2 theta, sine 2 theta, and cos 2 theta, and it's of 1k 0, 1 like this. And we are going to say minus I. I is the identity matrix. So 1 0 0 1 here. All right. So we can multiply the two matrices here. So that's cos 2 theta times 1, and it's plus minus sine 2 theta plus 0, which will just give us cos 2 theta. But there's a minus 1 here, so I'll say minus 1. Next, I'll say row by column. So cos 2 theta times k, which is k cos 2 theta. And here, minus sine 2 theta times 1, that's minus sine 2 theta. And it's minus 0, so it'll just be like that. Row by column, sine 2 theta times 1, that's sine 2 theta. And cos 2 theta times 0 is 0, and it's minus 0, so it's just fine like as it is. Then row and column, that's sine 2 theta times k, which is k sine 2 theta, and it's plus cos 2 theta times 1, which is cos 2 theta, and it's minus 1, so minus 1. So this is what we have right here. Okay, now we need to simplify this. Okay, so they say here that M minus I is singular, which means that we need to find the determinant of M minus I and equate it to 0, because we know that singular matrices have their determinants equal to 0. So we're going to say here, multiplying this 2, we'll be having cos 2 theta minus 1 of k sine 2 theta plus cos 2 theta minus 1, and it's minus the product of this 2, which will be sine 2 theta of k cos 2 theta minus sine 2 theta, like this. So let's simplify this. All right, I'll start with cos 2 theta multiplying the second bracket. So that will give us k sine 2 theta cos 2 theta, and it's plus cos squared 2 theta, and it's minus cos 2 theta. Then minus 1 multiplying the second bracket, it's minus k sine 2 theta, and it's minus cos 2 theta, and it's plus 1. Next up, I'll have minus sine 2 theta multiplying this bracket, so that will be minus k sine 2 theta cos 2 theta, and it's plus sine squared 2 theta. All right, now we can see that k sine 2 theta cos 2 theta minus k sine 2 theta cos 2 theta add up to give us 0. So these two add up, and we also have here cos squared 2 theta and sine squared 2 theta adding each other up, and they will give us 1. Then we have minus cos 2 theta minus cos 2 theta, which is minus 2 cos 2 theta. All right, then we also have here minus k sine 2 theta, so minus k sine 2 theta, and that's plus 1, so plus 1. And remember, everything has to be equal to 0. Okay, we're saying that the determinant is equal to 0 because it's a singular matrix, right? 1 plus 1 is 2, so basically it's 2 minus 2 cos 2 theta minus k sine 2 theta equal to 0. Now we're going to use here double angle formulae. We have here 2 minus 2, and for cos 2 theta we can use the formula 1 minus 2 sine squared theta, and it's minus k sine 2 theta, which is 2k sine theta cos theta, and it's equal to 0, right? So good thing about this is when we simplify, we will get a 2 minus 2, so we will eliminate the 2's here, and here it will be plus 4 sine squared theta minus 2k sine theta cos theta equal to 0. 2 minus 2 is 0, which is a good thing. And here we can factor out 2 sine theta. Inside the bracket we'll now be having 2 sine theta minus k cos theta equal to 0. All right, which means either 2 sine theta is equal to 0, or 2 sine theta minus k cos theta is the one that's equal to 0. And here, if we divide everything by cos theta, all right, we will be having right here, this will be 2 tan theta minus this becomes k is equal to 0. So the question is saying here we should find the value in terms of k of tan theta. So we can make tan theta the subject here to say that tan theta is equal to k over 2. So this here is the answer. That's the answer they want. Let's move on to part D. It says, given that k is equal to 2 root 3 and theta is equal to 3 pi, show that the invariant points of the transformation represented by m lie on the line 3y plus root 3x equal to 0. Okay. All right. So we have here the matrix M. All right. The matrix M, I'll take this and I'm going to paste it down here. So here is the matrix M. Okay. And we can say here that the matrix M is equal to, and here they say that theta is a 3 pi. So it's as good as we have cos of 2 3 pi. and it's minus sine of 2/3 pi, and it's sine of 2/3 pi, and it's cos of 2/3 pi. All right, and they also say that k is 2√3, so we have 1, 2√3, and 0 and 1 here. All right, now here for cos of 2/3 pi, we get minus a half, so it's as good as here we have minus a half, and also minus a half here. Then for sine of 2/3 pi, we get √3/2, so we have minus √3/2 here and √3/2 here, and these two are multiplying 1, 2√3, 0, 1. All right, so row and column will be having minus a half plus 0, so that's minus a half. Then row and column, that's minus a half times 2√3, which is minus √3, and minus √3/2 times 1, which is minus √3/2. All right, and here √3/2 times 1, that's √3/2, and minus a half times 0 is 0. Then lastly, √3/2 times 2√3, and that gives us 3, so it's 3, and minus a half times 1 is minus a half. All right, so eventually we will be having minus a half, then minus √3 minus √3/2 becomes minus √3/2. All right, and here we have √3/2, and here we have 3 minus a half, which is 5/2, like this. Okay, so this is what we have for M. All right, and now they say that they want us to show that the invariant points of the transformation represented by M lie on this line. All right, so if we take the matrix M, which is this, and we multiply it by the points x, y, and considering that we have invariant points, the image will still come out as xy. Okay, so we can say here, multiplying row and column, we get minus a half of x minus 3√3/2 of y, and this is equal to x. So that's the first equation we get. All right, and the second one is row by column, so that's √3/2 of x plus 5/2 of y is equal to y. Okay, so for this first one, if we multiply all the terms by 2, we will get minus x minus 3√3 of y equal to 2x. And here, what do they want us to show? They want us to show that it lies on the line 3y plus √3x equal to 0. Okay, so we can take the 2x to the left so that it becomes minus x minus 2x, which is minus 3x, and that's minus 3√3 of y equal to 0. And we can divide these by minus 3, like both sides. And when we do, we will be having here x plus √3 of y equal to 0. Okay, that's what we'll be having here. And that's one of the equations we get. Next up, we look at the second equation. So I'll multiply each of the terms by 2. And here we'll be having √3 of x, and here 5y, and here 2y. All right, if we take everything to one side, we will be having √3 of x, and here it will be plus 3y equal to 0. Now, what we have gotten here is what they want us to prove. That's 3y plus √3x equal to 0 if we rearrange, and that's actually what they have here. So I'll say shown. Let's move on to question number 5. It says, show that the curve with Cartesian equation x squared minus y squared equal to a, where a is a positive constant, has polar equation r squared is equal to a sec 2 theta. Alright, so here we have x squared minus y squared equal to a, and we know that x is r cos theta, so it's squared, minus y is r sine theta and squared, and it's equal to a. Okay, so it's like we have r squared cos squared theta minus r squared sine squared theta, and it's all equal to a. Factoring out r squared, we'll be having cos squared theta minus sine squared theta equal to a, and cos squared theta minus sine squared theta is actually cos of 2 theta, and it's equal to a. So I've used double angle formula here. Alright, so dividing both sides by cos 2 theta, we'll be having r squared being equal to a over cos 2 theta, and we know that 1 over cos 2 theta is sec 2 theta, so it's as good as we have a of sec of 2 theta shown. Let's move on to part B. It says the curve C has polar equation r squared is equal to a sec 2 theta, where a is a positive constant for values of theta between 0 and a quarter pi. So on part B, sketch C and state the minimum distance of C from the pole. Alright, so here we are considering that we want to sketch the polar curve r squared is equal to a sec 2 theta. Now here I'll make r the subject so that its r is equal to the square root of a sec 2 theta, which is as good as the square root of a over cos 2 theta, which is root a over root cos 2 theta, and considering that the range of values is between 0 and a quarter pi, where a quarter pi is not included, I will divide the range from 0 to a quarter pi into 3 intervals, and that will mean that I'll be going in pi over 12 increments, so 0, pi over 12, pi over 6, and pi over 4. And with these values, I'll make a little table of values where I'll be having the values 0, pi over 12, pi over 6, and since pi over 4 is not included, I'll use a value that is slightly less than pi over 4, which is 0.7. So when theta is 0, r will be root a, and when theta is pi over 12, r will be 1.1 root a. When theta is pi over 6, r will be 1.4 root a. And lastly, when theta is 0.7, r will be 2.4 root a. So I can now plot the points on the polar plane, and the graph will come out like this. Alright, so I'm gonna place the graph here. So we have the initial line here, and this is the pole. The initial line is theta is equal to 0, and the graph is coming out to be like this. Alright, so the question also says we should state the minimum distance of C from the pole. Alright, so the minimum distance of C from the pole is the distance from the pole to this point here. And this point is when theta is equal to 0. And when theta is 0, we discovered that r will be equal to root a. So root a is the minimum distance of C from the pole. Let's go on to the next part. On part C, they say, find in terms of A, the exact value of the area of the region enclosed by C, the initial line and the half line theta is equal to a 12th pi. You may use any result from the list of formulae MF19 without proof. So here we are going to make use of the equation of the polar curve. So this one here, and I'm going to paste it down here. And we're looking for area enclosed, and we know that area enclosed is found by the integral from alpha to beta of half r squared theta d theta. So in our particular case, we are saying that it's a equals to the integral, and the limits are from 0 to a 12th pi as given, and it's half of r squared. Now r squared is a sec 2 theta, so a sec 2 theta with respect to theta. So this will be equal to half a, and that's half a of the integral from 0 to a 12th pi of sec 2 theta, and it's with respect to theta. Right, so now they say here that we may use, now to integrate sec 2 theta, we will need to go to the list of formulas, MF19. Okay, so let's go there, and I'll scroll down to integration. And here you can see that if we integrate sec x, we get ln of sec x plus tan x, or ln of tan of half x plus a quarter pi. So let's take this, and I will paste it here so that we can make use of it. So this is going to be equal to half of a, and now integrating sec 2 theta, that's going to be here, since we have 2 theta, we'll be having 1 over 2, and I'll use the first one, so that'll be ln of sec, here for x we have 2 theta, so it's sec of 2x plus tan of 2x. All right, so this is what we have, and we are going to have the limits from 0 to pi over 12. All right, so we can simplify this. Here we have a quarter of a, and we have inside the bracket ln of sec of 2x, which is 2 of pi over 12, which is pi over 6, and it's plus tan of pi over 6, and it's minus, here that will be sec 0, and here it will be minus tan 0. Okay, so this is what we'll be having. So it's a quarter a of, here for sec pi over 6, that's like 1 over cos pi over 6, which is 1 over root 3 over 2, so it's like 2 over root 3. Actually, it's all under ln, so it's ln. Okay, everything here is under ln, so it's ln of 2 over root 3, and it's gonna be plus, here for tan of pi over 6, that's 1 over root 3, so 1 over root 3, like this, and sec 0 and tan 0 are 0, so it's fine as it is. All right, so here a quarter a and ln, and adding this 2 up, we will get 2 plus 1, that's 3, so it's 3 over root 3. All right, but I'll need to rationalize the denominator, so I'll multiply this by root 3 over root 3. So it's as good as we have a quarter a ln of this will become 3 root 3 over 3, which is as good as root 3. And here it's as good as we have a quarter a ln of 3 to the power of a half. And we can take the half using the law of logarithms, so that it's a quarter a times a half, and it's ln 3, which eventually will give us 1 over 8 of a ln 3. So this is the answer we get for this particular question here. Let's move on to the next one. So question number 6, it says the points A, B, C have position vectors I plus j minus I plus 2j plus 4k and minus 2i plus j plus 3k respectively relative to the origin. On part A, find the equation of the plane ABC, giving your answers in the form ax plus by plus cz equals to d. Alright, so in this particular case, they want us to find the equation of a plane, and we have been given 3 points that are on the plane. So we have their position vectors here. So what we're going to do is we are going to start by finding 2 vectors that are on the plane. So we might find the vector AB, and for AB we can find it by OB minus OA, and OB is minus I plus 2j plus 4k, and that's minus I plus j. Alright, so here this is going to be minus I, which is minus 2i, then 2j minus j, which is j, then 4k here. We will also find AC, which is another vector that is on the plane. We find this by OC minus OA. Now for OC, we have that here as minus 2i plus j plus 3k, and we are saying that's minus OA, which is I plus j. So this is going to be minus 2i minus I, which is minus 3i, j minus j, that's 0, then we're left with a 3k, so it's plus 3k. So we now have 2 vectors that are on the plane, and with these 2 adjacent vectors on the plane, we can now be able to find the normal, that's the normal n to the plane. So to find the normal to the plane, we will have this, that's I, j, and k here. So for the vector AB, the scalars are minus 2, 1, and 4. Then for AC, that's minus 3, 0, and 3. Alright, so we are going to close out I, which means we are left with 1, 4, 0, 3. So the determinant of that will be 1 times 3 minus 4 times 0, which is just 3. So we have 3i. Then we'll close out j, which means that we'll be left with minus 2, 4, and minus 3 and 3. So the determinant of that will be minus 2 times 3, which is minus 6, and that's minus 4 times minus 3, which is minus 12. So basically, we'll be having that as plus 6j, but considering the signs, we will put a minus on it, so it's actually minus 6j. Then closing out 4k, we are left with minus 2, 1, minus 3, 0. So the determinant of that will be minus 2 times 0 minus 1 times minus 3. And this gives us 3. So it's 3k. Alright. So this here is the normal to the plane. Alright. Now making use of r dot n is equal to a dot n, we can say here r dot, and for n, that's 3i minus 6j plus 3k, and that's equal to a dot n. Now a is a point on the plane. Now the point on the plane, we can use any one of the 3. Let's use the first one, which is I plus j. So I'll write that in column vector form. So for I plus j, that's actually 1, 1, 0, and it's dot. For n, that's 3 minus 6, 3. So 3 minus 6 and 3. Alright. So this is going to be equal to, here 1 times 3 is 3. Then 1 times minus 6 is minus 6, and 0 times 3 is 0. So we basically have 3 minus 6, which is minus 3. So we have here the equation of the plane being r dot 3i minus 6j plus 3k being equal to minus 3, which is in Cartesian form 3x minus 6y plus 3z is equal to minus 3. So we can divide each one of these terms by 3 since they are all divisible by 3, and we will get our final answer as x minus 2y plus z equals to minus 1. So this here happens to be the answer. That's the equation of the plane required. Let's move on to part B. On part B, the question says, find the perpendicular distance from O to the plane ABC. Alright, so you need to understand that if you have the equation of a plane, say being r dot n equal to d, then the perpendicular distance of the plane from the origin is found by d over mod n, and it has to be an absolute value, so we can just use an absolute value here. So this is quite important. So therefore, in this case, this perpendicular distance is equal to d, which in our case is minus 1, and that's over the square root, and that's the square root of n. Now n, if we look at the Cartesian equation that we have, we will take the coefficients of x, y, and z. So that will be 1 squared plus minus 2 squared plus 1 squared. And all this is under modulus, such that we'll be having 1 over the square root of 1 plus 4 plus 1. So basically, this is 1 over root 6. And this here is the answer. Let's move on to the next part. On part C, it says, find a vector equation of the common perpendicular to the lines OC and AB. So in this case, we have two lines OC and AB. So I'll just make a sketch. Let's say this is OC and this is AB. So OC and AB. And they want us to find the common perpendicular. So we can have a line which is a common perpendicular to both. So it makes a right angle with OC and makes a right angle with AB. Alright. So we're going to say let this common perpendicular meet the line OC at P and the line AB at Q. And now we'll need to find the vector equations of the lines OC and AB. So starting with OC, the vector equation should be r is equal to, and we should have a point on OC, and since it's passing through the origin, a point can be 0, 0, 0, and it's plus lambda of OC, that's the direction of OC, and we have that right here to be minus 2i plus j plus 3k, so that's minus 2, 1, 3. So we have right here minus 2, 1, 3. Then for the line AB, we have that as r is equal to, and here we'll need a point on the line. So let's take the position vector of A, and the point A is I plus j, so that's 1, 1, 0. So we have right here 1, 1, 0, and I'll say plus mu, and now we need the direction vector of AB. Now we have found AB here as minus 2, 1, 4. So I'll have that here as minus 2, 1, 4. So now that we have the vector equations of the two lines, we can now find the position vectors of P and Q. So I'll start with OP, and we are going to say for some value of lambda, OP will be equal to minus 2 lambda, lambda, and 3 lambda. And S4 the position vector of Q, that's OQ, we'll say for some value of mu, OQ will be 1 minus 2 mu, 1 plus mu, and 4 mu. So now we can find PQ, and we know that PQ is OQ minus OP, which will then give us, for OQ, that's 1 minus 2 mu, 1 plus mu, and 4 mu, and that's minus OP, which is minus 2 lambda, lambda, and 3 lambda. All right, so we are going to say here that PQ, actually let me put it here to save on space. So this will give us for PQ 1 minus 2 mu plus 2 lambda. Okay, and here that will be 1 plus mu minus lambda, and the last one will be 4 mu minus 3 lambda. All right, so this is PQ for us. Now PQ is perpendicular to both OC and AB, so we can say that the dot product of PQ with OC should give us 0. Remember, for perpendicular lines, their dot product should be equal to 0. Same applies with the dot product of PQ and AB. This dot product should give us 0. Okay, so let's start with PQ dot OC. So we will have PQ here. All right, so for PQ, it's this vector here. Let me write it down. So here it is, and it's dot OC. OC is the direction vector of C, which is minus 2, 1, 3. So we have minus 2, 1, and 3. So this dot product should give us 0. Okay, we'll also have PQ dot AB. So PQ is this vector here, and it's dot AB, the direction AB is minus 2, 1, 4. So minus 2, 1, 4 right here, and this is equal to 0. Okay, so let's simplify what we have, starting with this dot product. So we'll be having minus 2 multiplying 1 minus 2 mu plus 2 lambda, then 1 multiplying this, so it's plus 1 of 1 plus mu minus lambda. Then we'll also have 3, so it's plus 3 of 4 mu minus 3 lambda. All right, and this is equal to 0. Then for this other one, I'll be having minus 2 multiplying 1 minus 2 mu plus 2 lambda, then 1 multiplying 1 plus mu minus lambda, and it's plus 4 of 4 mu minus 3 lambda equal to 0. Now for the first one, multiplying the brackets, we'll be having minus 2 plus 4 mu minus 4 lambda plus 1 plus mu minus lambda plus 12 mu, and that's minus 9 lambda equal to 0. Okay, and starting with the terms in mu, that's 4 mu plus 12 mu, which gives us 17 mu. And for the terms in lambda, that's minus 4 lambda minus lambda minus 9 lambda, which gives us minus 14 lambda. Next, we have the numbers minus 2 plus 1, which is minus 1, and we cross it over to the other side and it gives us 1. So I'm going to call this equation 1. For the other one, we'll be simplifying it to get minus 2 plus 4 mu minus 4 lambda plus 1 plus mu minus lambda plus 16 mu minus 12 lambda equal to 0. Okay, so for the terms in mu, we have 4 mu plus 16 mu, which gives us 21 mu. Then we have, for the terms in lambda, minus 4 lambda, minus 12 lambda, which is minus 17 lambda. For the constants, we have minus 2 plus 1, which is minus 1, and we cross it over to the other side, and we get 1. Okay, so I'm going to call this equation 2. Alright, so we are going to solve these equations simultaneously. So I'm going to take equation 1, and on equation 1, I am going to make mu the subject. And if we do, we'll be having 14 lambda plus 1 over 17. And we're going to substitute that into equation 2. So on equation 2, that will be 21. And on mu, we put 14 lambda plus 1 over 17. And that's minus 17 lambda equals to 1. Alright, so here we will say 21 times 14, that's 294 lambda, and 21 times 1 is plus 21, and each one of them is over 17 basically, and that's minus 17 lambda equal to 1. Alright, and from here I will say 294 lambda over 17 minus 17, and this will give us 5 over 17 of lambda, and it's equal to, here I'll say 1 minus 21 over 17, which is minus 4 over 17. So basically we will get lambda coming out as minus 4 over 5. Now for mu we'll say mu is equal to 14 of lambda, which is minus 4/5 plus 1 all over 17. So we can do the calculation, and we get minus 3/5. So we have minus 3/5 for the value of mu. So we now have the values of mu and lambda here. So now the question is saying we should find a vector equation of the perpendicular to the lines OC and AB. So in other words, we're looking for the vector equation of PQ. So we are saying for the vector equation of the common perpendicular, which we have labeled to be PQ, so that's PQ, we will say that it's equal to, R is equal to a point on the line, which we're going to take the point P, so OP, plus a constant, let's use the letter T, times the direction vector PQ. Alright, now OP, okay, we want to start by finding OP. So let's start with that. OP is this vector here. Okay, so I'm going to take this and I'll paste it down here, which means it will be equal to, here, that's minus 2 times lambda. Lambda is minus 4/5, so it's times minus 4/5. Then lambda is minus 4/5, and that's 3 times lambda, which is minus 4/5. So OP will be equal to 8 over 5 minus 4/5 and minus 12 over 5. Okay, now just to simplify it a little, I am going to factor out minus 4/5 from it, which means I'll be having here 2, actually minus 2, 1, and 3. So this here is OP. All right. We will also need PQ. So let's talk about PQ. Now for PQ, we are going to have it as this. So I'm going to copy this and I'll paste it down here. So this is going to be equal to, and I'll substitute, starting with the first row. That's 1 minus 2 mu, so that's 1 minus 2 times mu, which is minus 3/5, and it's plus 2 lambda, which is 2 times minus 4/5. Next one is 1 plus mu, which is minus 3/5, and it's minus 4/5, which will be plus 4/5. Third one is 4 mu, which is 4 times minus 3/5, and it's minus 3 of lambda, which is minus 4/5. So this is what we have. So let's do the calculations, starting with the first row. And here we get 3/5. Second row, we get 6/5. And the last one, we get 0. And we can actually factor out 3/5, and we get it simplified as 1, 2, 0. All right, so therefore, for the vector equation, it will be R equals to, and for OP, we'll take this. All right, so that will be minus 4/5, and that's of minus 2, 1, 3. All right, and it's plus t, the parameter of, here we'll take the simplest ratio. Okay, we can ignore the scalar. Let's take the simplest ratio of our vector, which is just 1 to 0. So 1, 2, 0. So like this. So what we have right now is the answer. And that's how we do it. On question 7, it says the curve C has equation y is equal to x squared plus 2x plus 1 over x minus 3. So on part A, find the equations of the asymptotes of C. Alright, so we start with the vertical asymptote, which happens when we set the denominator to 0. So that's x equal to 3. Next up, we can talk of the oblique asymptote, because we can see here that the degree of the numerator is 1 greater than the degree of the denominator. So we can have the oblique asymptote. We will have to find that by dividing x minus 3 into x squared plus 2x plus 1. So x into x squared, that's x, and x times this, we get x squared minus 3x. Then we subtract here x squared minus x squared, that's 0. 2x minus 3x, that's 5x, and we bring down the 1. Then x into 5x, that's 5. 5 times this, that's 5x minus 15. Then we subtract here, and we will get 1 minus 15, which is 16 here. Okay, so the quotient gives us the equation of the oblique asymptote. So that's y is equal to x plus 5. So these are the two asymptotes. Okay, let's go on to part B. They say find the coordinates of the turning points on C. So we have the equation here. That's the equation of the curve C, and they want us to find the coordinates of the turning points. That means that we'll need to find dy by dx, right, and equate it to 0 since we're talking about turning points. So that's equal to x minus 3 times the derivative with respect to x of x squared plus 2x plus 1 minus x squared plus 2x plus 1 times the derivative with respect to x of x minus 3. All right, and that's divided by now x minus 3 squared and equal to 0. So I've done differentiation of quotients here. So this is going to be equal to, multiplying this to both sides, we get 0. So we just have the numerators x minus 3 of 2x plus 2. And that's minus, here we'll be having x squared plus 2x plus 1. And differentiating x minus 3, we get 1. So it's as good as that. And the denominator here will multiply to both sides and we get 0. So we just say this is equal to 0. So expanding brackets here, we get 2x squared minus 6x, all right, plus 2x minus 6. And that's minus x squared minus 2x minus 1 equal to 0. So 2x squared minus x squared is x squared, and minus 6x plus 2x, that's minus 4x, and minus 4x minus 2x is minus 6x. And for the numbers, minus 6 minus 1, that's minus 7, or equal to 0. Alright, so here we can factorize. And if we do, we'll be having x here and x here, and 7 and 1, then minus 7 and plus 1. Okay, so the values of x we get are minus 1 or 7. All right, now when x has these values, we can say here x and y, and x is minus 1 and 7. So the corresponding values of y, when x is minus 1 here, it will be 1, and that will be minus 2 and plus 1, which is 0. So the whole thing becomes 0. Okay, and when x is 7, that will be that's 16. So we have 16 here. So the coordinates of the turning points are minus 1, 0, and 7 and 16. So that's the answer to part B. Let's go on to C, where they say sketch C. All right, so let's do the sketch. I'll have the axis here. So that's y, and this here is x. The origin is here. All right, and the asymptotes, we have x equal to 3 and y is equal to x plus 5. So let's start with x equal to 3, which is this vertical line. So it intercepts at 3, and we have y is equal to x plus 5, like this. So it intercepts the y-axis at 5, and the x-axis at minus 5. All right. Now, we have been given that there are turning points at minus 1, 0, and 7 and 16. Okay. So the curve will be like this on this part with the turning point. Okay. And the other turning point is at minus 1, 0. So it should be like this. So there's a turning point somewhere around here at minus 1, 0. So like this. So this point here should be at minus 1. Okay. So this here is how the curve should be like. Okay. Let's go on to part D. On part D, they say, sketch the curves with the equation y is equal to mod of the function and y squared is equal to this on a single diagram. Okay. And they say clearly identifying each curve. All right. So let's start with the modulus graph. Okay. Actually, I'm just going to make a copy of this whole graph. So copy, and I'll paste it down here. Okay. So we have this curve. So let's start with the modulus graph. With the modulus graph, we will reflect the part of the curve that is below the x-axis in the x-axis. So we can reflect this. All right. So it'll come out like so. Here I'll use a different color, red. Okay. So this is the reflected graph. So next, for the graph of y squared is equal to x squared plus 2x plus 1 over x minus 3, we will consider the part of the graph that is above the x-axis, which is this curve here. And we know here that the turning point for this point is 7 and 16, all right? So this here is 7 and 16, all right? And for the graph of y squared equals to the function, we will have the turning point at square root of the y value, square root of 16. So it will be at a point 7 and 4, which means the turning point will now be here. So I'll use a different color. So same x value, but different y value, it will be a root. And all the other y values of this curve, okay, will be square rooted, which means they will have lesser values, okay? So basically this graph will move downwards for that reason, okay? So the graph will be like this with a turning point at 7 and 4 here. So this little turning point is now at 7 and 4, all right? And all the other parts of the graph have their y values square rooted, which means that the graph is like coming down like this. So once we have this part, we will now reflect it in the x-axis, which means we can have the same thing happening down here where we have a turning point. So more like this. So we now have the graph of y squared like this, okay? Now I'm going to remove this other original graph, which we no longer need. So here I'm going to remove this other part from the original graph, and this is the origin and the point -5 as we originally had. So this is what we have for the two graphs. So the graph in red, including this line segment, is the one for modulus, and the one in blue is the one for y squared is equal to the function. So that's how we do it.